Did you ever find yourself hunting down dependencies through dozens of files, even though you just wanted to add a simple, small feature? Well, I've surely been there more often than I'd like to admit. Sometimes I even had to throw away lots of code for an almost finished feature because implementing it in a proper way would have just destroyed the rest of the application. So I took the quick and dirty route, and it always felt bad. But here's the catch. Most of the time, the application code that I wrote was totally fine. The problem was the project's architecture, or should we better say, the lack thereof. And this is exactly where clean architecture comes in. Today we'll take a look at it by the book, and also how I adapt it for my real-world projects. And all throughout the video, we will follow a concrete example, which is an e-commerce platform, so that you can see those principles in action and not just in theory. And finally, to top it all off, I will share with you my Axum template project so that you can start with clean architecture today. So, let's dive in. Clean architecture was popularized by Robert Martin, who is better known as Uncle Bob, in his book, which is also called Clean Architecture. And most often it gets sketched out as those 4 concentric circles. The individual circles represent layers in the code, and the boundaries between these layers are what's most interesting, because dependencies are only ever allowed to flow inwards. So, for examples, the adapters layer is allowed to depend on the application and the domain layer, but not the other way around. In the book, this is called the dependency rule, and it is the base principle of clean architecture. Break it, and you get a big ball of mud. I'll go into what these layers should contain in a second, but first, let's talk about the benefits of layering your application. The layers are sorted by their purpose and their level of independence. Both these metrics increase the further we go to the center. The core is what fulfills the customer's needs, or you could say it solves the problem of the business domain. So it needs a certain amount of freedom to do this task efficiently, and therefore, it should be as independent as possible from all the other aspects of our application. The infrastructure, on the other hand, is a detail. It's merely a means to an end, and as such, it has to serve the core. As we will see, following this layered approach, together with the dependency rule, produces applications that are easy to maintain, extend, and test. But now, let us get into the meat of this. The most central layer is called the domain layer. This is where all our business domain logic lives. It mostly consists of entities and domain services. Entities are the central players in the application, and domain services are elementary interactions between the entities or on the entities themselves. Because the domain layer is at the center, it must not have any dependencies on the outside layers. Note that bringing in a few very simple crates here, like a UUID, is okay though, but don't add frameworks, databases, or anything alike to this layer. If you're not sure what should go into this layer, ask yourself, could this piece of code be reused in a different application within the same business domain? If the answer is yes, then it's probably a good idea to fit it in the domain layer. In the realm of an e-commerce solution, some domain layer entities would be a customer, a shopping cart, or an item. Adding an item to a shopping cart is an elementary interaction between entities and could therefore be a service. Next up is the application layer. It contains all the business logic which is specific to this very application. Most of what you will see in this layer are use cases. A use case is the implementation of a typical action in the business domain, which interacts with the entities and orchestrates multiple domain operations into a single process. Of course, this means that the application layer is dependent on the domain layer, which is in agreement with the dependency rule. The important invariant of this layer is all the code is still independent of the delivery mechanism, frameworks, and technical details. Again, there is no Axum, Tokyo, Postgres, or Serde in this layer. In our e-commerce example, a use case could be the whole procedure of placing an item in a customer's shopping cart, which includes first checking the item's availability in the inventory, then reserving the item, and finally adding it to the shopping cart. Note that the individual actions in this use case are services provided by the domain layer, but the overall process is specific to this application. Think of it like this. If instead of an e-commerce shop, we would be building an online auction platform, customers couldn't just add an item to their cart. Instead, we would provide use cases for placing a bid and finalizing an auction. However, we could still use some of the same entities of the domain layer, like the customer and the item. I personally like to view the application and the domain layer as the core of a project. What they have in common is that they are fully independent of frameworks, infrastructure, and the concrete I/O. The core provides the same functionality no matter the delivery mechanism, like in a web application or CLI or a native app. In some applications, the line between domain and application layer can be quite blurry though, especially if you have only one project on this domain, and thus reuse of the domain layer is not a priority. And even though it might be tempting to just merge both into a single layer, I prefer to keep them separate. It just gives more structure to the project layout. Right outside the core, we have the adapters layer. As it is described in Robert Martin's book, this layer converts between domain data formats and external representations. What you will typically find here are controllers, presenters, and gateways. It is this layer which connects your core to the real world, where your infrastructure sits. Some examples are the conversion from a shopping cart, which is our domain entity, to a data transfer object, serialization and deserialization, as well as creating a timezone-aware datetime string from an internally used timestamp. And finally, the infrastructure layer is on the outer rim of this architectural pattern. It contains all the concrete technologies which the use cases rely on. These can work on their preferred data formats thanks to the adapters layer. What we find here are devices, databases, all the frameworks, etc. And as it is mentioned in the book, we typically don't write a lot of code in this layer ourselves. Example infrastructure components are Axum endpoints, Tokyo, Postgres queries, etc. At least, this is how I understood it from the book. And let me tell you, I read those few pages in question at least 10 times. But what didn't make sense to me is the following. How can the adapters layer be independent of the infrastructure layer if it needs to adapt the core to the infrastructure? Because this is exactly what the dependency rule states, right? Dependencies can only flow inward, so the adapters layer can never know the infrastructure. To me, an adapter only makes sense if it knows both sides. I mean, think of this. If my frontend requires the shopping cart contents in JSON format, I need to write an adapter that converts the domain representation into exactly that format. That's even what the book says. I cite from page 205. The software in the interface adapters layer is a set of adapters that convert data from the format most convenient for the use cases and entities to the format most convenient for some external agency, such as the database or the web. So, for me personally, the outermost dependency arrow just doesn't make sense. So, instead I like to structure the outer two layers a bit differently than is outlined in the book. I renamed the adapters layer to infrastructure-aware adapters. This makes it clear that the adapters do actually depend on the concrete infrastructure used. This layer contains the glue between the core and the infrastructure, and it is made up of request handlers, DTOs, database access functionality, and so on. The adapters drive the use cases and might do some technical orchestration as well. It is the adapters layer in which we bring in the external dependencies we didn't want in our core, like Axum, Tokyo, Serde, SQLX, etc. Some typical examples would be HTTP endpoints, serialization and deserialization, although that is probably mostly handled by Serde anyways, or database access routines. I also made it clear in the visuals that this layer is oftentimes way larger than the infra and setup layer. And finishing up with this modified approach, the outermost layer actually doesn't really have a lot of code. It's mainly setup and configuration, like establishing a connection to the database, building the app state, or injecting some dependencies. And of course, all the actual third-party crates and technologies also go here. So you can consider your cargo.toml file as the manifest of your infrastructure choices. Now this layering makes much more sense to me. But let me know about your experience here. Maybe I just misunderstood a few paragraphs in the book, who knows. But now, time for a little example. I chose the process of adding an item to a customer's cart for an e-commerce site as an arguably just complex enough showcase. I hope this will clarify the theory we just went over and hint at some challenges in the design. And an important note, all arrows shown here represent the flow of control, which does not in general coincide with the dependency direction. So please keep that in mind. The whole process starts with an HTTP request that might be coming from the front-end client. It is received by Axum and routed to the add-item-to-cart endpoint sitting in the adapters layer. With this request, we received the minimal required payload, a customer ID and an item ID. What the front-end client eventually expects as a response is the customer's updated cart inventory, delivered in JSON format as part of the HTTP response body. But we still have a way to go before we can respond. In order to process the client's requests, the Axum endpoint calls upon a use case in the application layer. Up until now, everything aligns nicely with the dependency rule. The outer layers know about the inner ones, but not the other way around. The use case will then execute, probably working on some of the domain entities. Finally, we need to persist the changes made to the customer's cart and our inventory. And for the sake of brevity, let's assume that those two things are enough to have a proper process. This requires us to make two calls to our database, one for storing the item to the cart, and the other one for persisting that the item is now reserved. What's happening here could be called business orchestration. Adding an item to a cart will always lead to reserving that specific item, such that it cannot be put in two carts at the same time. No matter our delivery mechanism, this is an invariant of our application, or a policy you could say. And that's why business orchestration happens in the application layer. As you can see, the use case we just called doesn't return the cart contents. And why should it? That's not required to add an item to a cart. But our endpoint in the adapters layer needs to return the updated cart inventory. And therefore, it needs to call a second use case, which returns a shopping cart entity. Again, we access our database to retrieve the relevant data for the cart. The Axum endpoint can then extract whatever it requires. This orchestration happens in the adapters layer because it is tied to the delivery mechanism. The front-end client expects to receive the updated cart inventory as part of the response. If we were to use our application core for a native app, this behavior might be different. Therefore, we could call this technical orchestration. To conclude this process, the Axum endpoint returns an HTTP response with the cart inventory to the front-end client. Now let's get into a bit of an analysis about what happens here. The arrows we drew show us the control flow. In the initial part, they point inwards, which is what we want. The outer layers call functionality in the inner layers, and that aligns perfectly well with the dependency rule. However, we also have outward-facing control flow. This happens when the use cases need to interact with the persistence, and when the endpoint returns an HTTP response. I colored part of those arrows in blue. This showcases exactly the point I made about the dependency rule between the adapters and the infrastructure layer. In theory, adapters shouldn't depend on the infrastructure, but in my practical approach here, they do. This means that when I change my database type, I'll have to rewrite part of the adapters. But since changes tend to ripple anyway, I find this trade-off acceptable in practice. The real problem shows when we take a closer look at how the use cases access the adapters. We definitely shouldn't break the dependency rule between those two layers. Again, the arrows only depict the control flow, not dependency. But without any abstractions, dependency and control flow direction will align. So we'll have to invert the dependency structure here to allow for clean architecture. I'll showcase how to do that by means of the getCart action. The use case wants to return a shopping cart entity, which contains a collection of all the items in the cart. Therefore, it needs to access the persistence to query these items. As an identifier, we use the customer ID. The problem now is that if we call the getCart contents adapter directly, the application layer depends on the adapters layer, which breaks the dependency rule. Structuring our code like this would mean that changes to our database infrastructure would ripple through the whole application layer. The solution to this problem is quite simple though. We create a trait called cart persistence in the application layer, which is tailored to the needs of the cart-specific use cases. Amongst some other functionality, it defines the getCartContents method. Traits like these are often called ports. The use cases can now rely on this trait, because they are part of the application layer and therefore independent of the adapters. Ports can also be found in the domain layer, by the way. Of course, some adapter on the other side now has to implement this trait in order for our application to work. Note though that the implementing adapter depends on the application layer, as this is where the trait is defined. Through this abstraction between the two layers, our design aligns with the dependency rule. This pattern is probably one of the most used techniques in software design. It is called dependency inversion because it lets us invert the direction in which the dependency flows. If you are new to software architecture, I can highly recommend this book, because it really goes into detail about some of the principles behind good software architecture in general, And it's very hands-on and easy to understand. And by the way, I'm not sponsored or affiliated with the book in any way. However, I know that clean architecture is not, by far not, the only way to structure your project. So let me know down in the comments how you structure your projects and what architectural patterns you prefer. And by the way, you're not breaking any architectural rules by leaving a like or even a sub. Just saying. But now let's finally take a look at some real code. I've set up an Axum project because personally this is what I prefer to use for web backends. But as soon as you've understood the principles behind clean architecture, you can apply this to any framework in most other languages, I'd say. This is the project template that I typically start out with when I want to do clean architecture with an Axum web server. So what you can see right away is I create, at least initially, one directory for each of the layers. When you go further into the project, you might want to have parent directories for certain features over that. Your decision. I start out with this. So I have domain and my application, adapters, and my infrastructure. In the domain itself, I left exactly one entity, and you will see that throughout all this template, there is only one process, which is the user registration, because that's typically more than enough to see how things are going to flow. But I didn't want to clutter up all this template with a lot of default processes that probably no one's going to use. My user entity here has an ID, and as I said, I am not against using small imports or small third-party crate in the domain and the application layer, because I see something like a UUID not as a framework or an infrastructure, but I see it as kind of an extension of the base programming language. And so I think this one is fine. Of course, you could use something else as a ID, your choice. Then I have a username, a password hash, and a date time when the user was created. Next is then, of course, the application layer. And here it's a bit more interesting than the domain, because not only do I have use cases here, but I also have some application-wide errors that I typically use. So at first, the user use cases. This is just a struct. This struct depends on both a hasher for the password stuff and some persistence, because of course, when a new user is being registered, then I have to persist it in some way. And because this is exactly the case that we talked about with the dependency inversion, I don't want to actively reach into the infrastructure where I get my concrete hasher and my concrete persistence, but instead I want to here have a port definition, which allows me to depend on only my own port definitions, but the adapter side will then come and implement some of those functionalities. So I have one trait, which is the user persistence, and it has the function to create a user based on some information that we feed into there. And then we have the user credentials hash, and in here we can hash the password. And you can see I take two trait objects behind an arc, because usually you want to go multi-threaded here, or at least you want to have concurrency with Tokyo. And therefore you want to be able to share those things between threads, so I have them behind an arc. We then implement our user use cases. So I've got one struct for each collection of use cases. Some people do also one struct per use case. So something like register user use case, then login user use case. You can do whatever you see fit, and depending on how large your structs become, that might be a decision you want to make. And here I have just the typical add function. So what we do, of course, is we take in, or we require all this information that a new user has to provide or has to have within itself. Then we hash the password, and I usually store passwords behind a secret, so I use secrecy to not accidentally lock any of those passwords, which would be a safety hazard. And then I'll go to the persistence part, or to the persistence trait object that I have stored, and just call create user. And then we'll just do some tracing and OK out. This is the very basic workflow that you would have in a use case. So you get some input. Typically it's like from the front end, but could be from any other UI, from any other user interaction. Then you might have to reach out to some abstract persistence or some abstract hasher and then you come back and return whatever you need to return. In this case, it's just an OK as a signal to say like, okay, the user was added. So the nice thing here is we can directly add tests here, which are, of course, unit tests, because I can mock all my dependencies. For example, here I have a struct mock user dependency, which will just test that some of my inputs are exactly hard-coded strings that I have here. And I can also mock my credentials hasher to just create some very, very safe hash of a password, as you can see here. And then you can write unit tests, something like this one here, add user works. And you don't need to spin up all your Postgres database. You don't need to have the adapters layer even working. You can just test your use cases. And you could, of course, do the same thing with your entities, which is a huge benefit because your application just becomes testable by default when you use clean architecture. And the one thing that you've probably seen already here is that I defined a custom app error. And this error just has some enum variants to kind of group general error segments into one single error. For example, everything that is an error from the database, I will just wrap my SQLX error, which is what I use for database access, into this database error variant. And I do the same thing, for example, with invalid credentials, or if there is some other internal error. And then, of course, I have a shorthand result, which is the app result. We can then move to the adapters layer, where we can already find our app error implementation. So, of course, what I do is I want to be able to return an app error from my Axum handlers, because this makes it very simple to just bubble up errors. And you can only return things from your Axum handlers that implement into response. So therefore, what I do is implement into response for app error. And here it's just a very, very simple match statement that basically maps each kind of an app error into some HTTP status code and maybe gives a bit more context. Of course, this implementation is in the adapters layer, not in the application layer, because in order to implement this, I need to import a lot of stuff from Axum already, and our applications layer should not be dependent on any infrastructure. Also, what I have here is the app state, which is Axum dependent. So you can see what I pack into my app state might be something like the config, which has general configuration settings that are maybe interesting for multiple parts in the app. And also I have my user use cases struct here so that all the Axum handlers can then just reference this user use cases struct. Inside here, I also have, of course, my routes. What we see here is the user routes. So every route will just define its own route. In this case, we just have the user register. And you can see that register defines its own payload here, which is what we expect to get from the outside, for example, from the front end. And then its response. Those are structs that have nothing to do with our application itself. This is bound to our delivery mechanism, so Axum. So this is all in our adapters layer. And then when we take this, we can call the user use cases, call add on it, await it, and then we just return the OK. You see here, in case user use cases fails, for whatever reason, we can simply just bubble up any errors, because this add method of user use cases returns an app result, and app result implements into response, and therefore we can just bubble it up here. So that's it basically for the Axum endpoints. I then merge all of my routes here in mod.rs in the routes directory. Of course, currently I only have one route, which is the user route. And then the only other thing I have here is the crypto module. I use Argon 2 for password hashing, but you can see here for the first time that Argon password hasher is one of the adapters that actually implements a port that I defined in the application layer. So this user credentials hasher was the trait or the port that I defined in the applications layer, and Argon password hasher implements all of this so that it can then be injected as a dependency, you could say, that lies behind user credentials hasher. The other thing I have here is the persistence layer. In here we have a struct that is called Postgres persistence. This is persistence adapter that will do all the Postgres stuff. In here, I have, of course, a pool of Postgres connections. And if we then look at the user.rs file, we can see the implementation. Postgres persistence implements our user persistence trait that was defined by the use cases in the application layer. And we can, like this, create a user. Again, we're returning an app result. Very, very basic SQLX query here. And you see all the errors that would be coming up here are mapped into an app error of variant database. So that's already the adapters layer. As you can see, a lot of the code is actually in the adapters layer because this is where all the technical stuff happens. The calling of the use cases, the error handling is a lot in here as well. So that's quite a large layer. What we're left with is our infrastructure layer. In here, as I said, what I like to do most is basically the setup. So for example, we have the DB. This is just how to initialize a DB. So I get the database URL from my environment variables. Then I set up a pool. Yes, the max number of connections could be some config, don't have to be. You can go into config. This is where I set up all my configuration. For example, I often do authentication by hand for smaller applications. So you would need some JSON Web Token secret here. You would need a time to live for the access token and for the refresh token. And this is just a way I parse this from my environment variables and then get my app config. In the setup here, what do I have? Well, I have a way to initialize my app state. So this is basically where the dependency injection happens, because this is where I decide which of the actual implementations I put behind my ports. So I decide here that I will instantiate a Postgres persistence to lie behind the user persistence, and also that I have an Argon2 hasher for my cryptography. And you can see the app state is then created down here. So the user use cases is created from this user use cases variable, and this one injects the Argon hasher and the Postgres. This is also where I initialize my tracing because I like that as telemetry. Overall, how are things knit together? Here in the lib.rs, I will define those 4 layers as my modules. And then in order to have a bit shorter use statements, I like to re-export at least the application and the domain layer here. And the main function then doesn't do a whole lot, actually. It starts reading the environment variables or initializing them, creating the app state, creating the app itself, binding the listener to a port, and then basically serving that. You can find this template down in a GitHub link if you want to take a closer look, if you want to modify it. If you have any improvements, feel free to shoot me a pull request. I'm totally open for that as well. I personally got into the code architecture game quite late, I'd say, and I do really regret that, because I thought that learning software architecture is a huge endeavor that takes forever and ever. But as it turns out, that's not the case. You can learn the basics of good software architecture in merely a few months, I'd say, and your code quality will massively benefit from that. So if you're also interested in learning more about architecture, then stay tuned on my channel. I see you next time with Green Tea Coding.